Looking at this map, we reach the final component of the foundational cognitive tier, the Memory-Augmented Agent. This layer makes AI stateful. We've examined the first two. Agent 1 executes immediate decisions. Agent 2 constructs plans to reach long-term goals. But both of these agents suffer from the exact same fatal flaw. When a session ends, their memory buffer clears. They wake up to the next project with total amnesia, possessing zero context about what happened the day before. Without a structural mechanism to carry context across sessions, true autonomy is impossible. If the agent forgets the user, every interaction is forced to start from zero, rendering those decision and planning capabilities entirely reactive. A common engineering crutch is to bypass memory architecture entirely by stuffing raw interaction logs into a massive 1 million token context window. But a larger context window is not a memory system. Stuffing the prompt is the equivalent of handing the model a massive, unorganized binder for every single query. It forces the LLM to scan thousands of irrelevant pages just to answer a simple question, driving up compute costs and actively degrading its reasoning capabilities. The solution is the tripartite cognitive state, 3 specialized layers. First, working memory, the sticky note for active session context. Second, episodic memory, the diary, storing a timeline of cross-session interactions. Finally, semantic memory, the encyclopedia, holding distilled factual knowledge. To maintain efficiency, the agent routinely performs memory consolidation. A human brain does not store the episodic log of every breakfast eaten over a decade. It distills that data into the semantic fact that the person likes eggs. The agent does exactly the same thing. Intelligent statefulness is not about hoarding raw data. An efficient memory system achieves scale by systematically retrieving, consolidating, and selectively forgetting information. This diagram illustrates the 6-stage closed cognitive loop that powers the memory-augmented architecture. Stage 1 is external inputs. This is where user queries, environmental events, and sensor data first enter the system to initiate the cognitive cycle. In Stage 2, that data hits the agent core. In Stage 5, the retrieval engine pulls the necessary history and facts from the episodic and semantic stores, bridging the gap between past events and the current query. Finally, Stage 6 produces the agent outputs. The response is generated, and the feedback loop routes the result back into the system to be permanently recorded. This specific feedback mechanism is the exact mechanical difference between a standard language model generating text and an autonomous entity learning from experience. The effectiveness of this loop relies entirely on how the agent searches its own history. Instead of relying on rigid keyword matches, vector retrieval searches by conceptual meaning. When a query arrives, the engine projects it into a mathematical embedding space. It ranks the surrounding historical data based on semantic similarity, recency, and user preference, surfacing the memories that actually matter. But leaving episodic memory unmanaged is highly destructive.
As raw interaction logs accumulate, query after query, the vector space becomes crowded, slowing the retrieval engine and degrading the accuracy of the similarity scores. To prevent this, an asynchronous consolidation pipeline constantly operates in the background. It reviews dozens of raw episodic logs and compresses them into dense, high-value profiles that require a fraction of the storage space. This consolidation pipeline is a mandatory maintenance layer. Without it, the agent's database inevitably bloats, and the architecture will collapse under the weight of its own history. To move from the theoretical loop to programmatic reality, we can inspect the process interaction method inside the Memory-Augmented Agent class. First, the episodic memory.search function executes the vector retrieval phase, querying the database using the raw user prompt. Next, the _format memory step takes those retrieved records and formats them for injection directly into the working memory prompt. With the context loaded, the llm.generate command fires, utilizing the agent core to reason over both the active session and the historical data to formulate a response. Finally, the asynchronous episodic memory.add function executes, writing the new interaction into the long-term episodic store for future access. By wiring standard vector database operations directly into the LLM's prompt cycle, engineers synthesize a stateful mind out of stateless APIs. In practice, this architecture solves complex continuity problems. In IT support,
An amnesiac agent will repeatedly ask a user if they have tried restarting their router. A stateful agent retrieves the user's previous escalations and custom enterprise architecture plans, moving straight to advanced diagnostics. In healthcare, a personalized assistant retrieves a patient's historical records regarding dietary restrictions and previous fatigue interventions, ensuring that current medical advice aligns with past treatment outcomes. But establishing strict engineering guardrails is critical. Memory-augmented agents should never be deployed for stateless one-shot triage tasks where history is irrelevant. They are also dangerous in latency-critical hot paths. Vector retrieval and context generation take time. Unless asynchronous write capabilities are strictly enforced, the memory layer will bottleneck the entire application. Finally, there is the privacy mandate. You must never store cross-session user data that cannot be rigorously governed, verified, and explicitly deleted upon request. Memory introduces immense capability, but it demands stateful complexity. It should be deployed exclusively when continuous context is a strict business requirement. Zooming out, we can now see the complete picture of the foundational cognitive triad. Agent 1 decides the immediate next move. Agent 2 plans for the future. And Agent 3 makes the entire stack stateful by looking backward. Yet Agent 3 has a distinct limitation. While it remembers the user's specific history perfectly, its general understanding of the world is permanently frozen at the underlying LLM's initial training cutoff date. To solve this, the architecture requires a massive upgrade. We must scale memory recall from tracking a single user conversation to retrieving specific facts across an entire enterprise corpus. That requires Agent 4, the Knowledge Retrieval Agent. To see the code for the memory systems we covered today, check out the book 30 Agents Every AI Engineer Must Build by Imran Ahmad, and follow the link to the next video in the series to explore Agent 4.